Yeah, I'm visiting from Los Alamos, and I'm sure everyone here is pretty familiar with that place. They do a lot of nuclear weapons research. They refine weapons-grade plutonium that gets used for positive things like rovers and for nefarious reasons. And yeah, I'm outside the fence. I don't have any clearance. You can only get clearance if you're a US citizen, generally. But yeah, I'll be talking about some of my work on protoplanetary discs, looking at how, well, let's just get into it, huh? Click. Yeah, okay. So just to give a really very basic introductory sort of slide on the structure of a protoplanetary disk to give some context. So protoplanetary disks are disks of gas and dust that exist in the early stages just after the star itself is formed. A very sort of basic image is that the disks themselves are flared. So you have the disk, it goes from, basically it goes from like a boundary from close to the surface of the star to some outer radius where there may or may not be a sharp truncation of the outer disk. The disk itself is flared, so there's like a surface of the disk that has a direct line of sight to the central star, so it gets illuminated, so you can see features in the disk if they exist. Dust grains, there's a mixture of dust and gas. The smaller dust grains, think like submicron sized dust grains, they basically get carried by the gas, just like, you know, in a dust storm here on Earth. Larger dust grains, though, they react differently. They experience drag forces, and so they settle in the disk. They settle towards the midplane of the disk. So when we look at an image of a protoplanetary disk, if we look at, say, the near infrared, we're looking at this surface of the disk here. But if we use a millimeter interferometer like ALMA, we're probing the thermal emission from these millimeter dust grains in the midplane. So it's kind of important for when you're looking at features of a disk, when you're looking at images of a disk and you see particular features. So quite a few protoplanetary disks have spiral arms in them, and here are a few of, I think, the most remarkable examples. The one on the left is AB Aurigae. It's a pretty massive star, two times the mass of the sun, and has this very, almost like looks like a rose nearly, very strongly perturbed protoplanetary disk around it with lots of spirals and yeah, crazy stuff going on. You can even see a little bit of shadowing here. There's this like little spiral here that's casting a slight shadow on the outer disk. Then we have, and this disk, by the way, has like a reflection nebula as well. So it's not just an isolated disk. It appears to be gas from the surrounding environment interacting with the disk, and they may be responsible for some of these spiral arms. There's a disk like MWC758 where we get these, it's a bit hard to see, but there's one spiral here, there's one spiral down here, and several other spirals on the outer disk. There's a disk like HD100 453 where we have this kind of depleted, well, this cavity where there's not much scattering from the dust grains, and then you see like the surface of the cavity with this ring, and there's shadows here cast by a misaligned inner disk, and these two prominent spiral arms that actually attach to a 0.2 solar mass companion that's in orbit around this disk. And another example where we have this depleted cavity. So there's a coronagraph in the front here. So it's like a disk that blocks the starlight, but the coronagraph's actually smaller than this inner cavity you see here. So it's a similar story to HD100 453 where you have this like sharp truncation of the inner disk and then spiral arms outside. So spiral arms themselves can be caused by pretty much any perturbation that happens to the disk. They can be caused by companions in the disk, such as planets, or say in AB Aurigae, where you have this infalling disk material that's perturbing the disk. Another commonly seen feature are rings, cavities, and gaps. So these can be seen in near-infrared images, such as here in TW higher, where so this is near-infrared. We're looking at the surface of the disk, the small dust grains. You can quite clearly see that there's a slight depletion here in scattering, and then followed by a bright ring, and then another drop in the scattered light intensity. All the rest of these images are millimeter wavelength images obtained by ALMA, and you can see that the morphology of the disks can vary quite substantially. So AS209, you have these very nice, neat concentric rings, and the disk appears to go all the way towards the central star. You have something like PDS-70, which has a sort of this big, thick ring around, followed by emission around the central star, and actually some emission from a circumplanetary disk. So there's a planet, there's actually two planets in here, one's right here and the other one's here that you can see. Those planets have basically carved out disk material and are preventing these millimeter-sized dust grains in the outer cavity from migrating inwards. And then you have a disk like HD 142527 where there's a confirmed stellar companion in this disk. So there's a very massive 0.2 to 0.4 solar mass companion around the central star, which is about 1.8 times solar mass. And you get this very depleted central cavity, and also this very striking dust horseshoe where we have an overabundance of dust grains on this side of the disk and a relative depletion on the opposite side of the disk. So in some cases, in some of these examples, we have a clear connection between confirmed planets or companions in the disk. So in PDS-70 and HD14, we know there's two planets in PDS-70. We've seen them, their accretion signatures. We know they're accreting. We can see the disk material around them. And then we have an example like HD14 where there's a stellar companion. The orbit, we don't know the orbit too well just yet, but it seems like that stellar companion can explain the shape of the cavity and the features that we see in it. So we have these examples where we know there's a companion, we can run a hydrodynamic simulation, and we can recreate the features we see in the disk. But in quite a lot of other disks, most other disks, we don't have any companion detections. And we are inferring, based on what we see, what might be causing these features. So those two previous things, the spiral arms, the cavities, the gaps, and the rings, they just show you like a snapshot image of what the structure of the disk is like. But we also get another third, incredibly, probably the most important bit of information we can get from protoplanetary disks, which is the velocity field. So we can get, hopefully that feedback is not too bad. So we can get, say, like an emitting molecule, like carbon monoxide. It gets warmed, it emits photons. And so what you see here in these like kind of butterfly patterns are the blue and red shifted sides of the disk. So the disks in most cases here are in fairly smooth Keplerian rotation. So here on the left and so HD163 and HD97. These are two examples of relatively unperturbed disks, and you can, So with carbon monoxide, it gets emitted on the surface layer of the disk. So in that previous picture, it's not coming from the midplane; it's coming from an elevated surface on the disk. So you can actually see that elevated surface here. We have other examples like HD100-546 and strikingly GG Tau. GG Tau is a quintuple system. It has a triple star system inside of a cavity, and it has another binary orbiting around it. And here is only the triple. There's a triple in here. The binary is like the exterior binary is somewhere down here. But you can see pretty clearly that GG Tau, the kinematics of GG Tau are very different to HD163, where there's strong perturbations across this inner cavity on the order of several kilometers per second. So the question is then, we have all of these disks, we have these really great observations showing us the structural features in them and giving us, and also the velocity information. And then in most cases, we don't know whether there are companions in these disks or not. But yeah, the goal of my research has been largely to, in these disks that we don't have companion detections, what can we infer? What kind of companions do we need to explain the morphological features? And in some cases, we see these features very early on in the evolution of the protoplanetary disks. So in the class 1 phase, so that means that like roughly 10 to the 5, a few 10 to the 5 times since the star itself is formed, and the disk lifetime is a few times 10 to the 6. So it's very early on. We see some of these features early in the evolution of the disk. All right, so as I mentioned before, pretty much any perturbation in a disk can generate spiral arms. So on the left panel here, I have imagine you're at Los Alamos and you're detonating a bunch of nukes. You're generating these wave patterns that are coming out radially, like splashing water in a pond. You generate these concentric rings. But if you make a similar perturbation in a rotating field, say in a disk around a protoplanetary, around a star, you generate spiral arms from that perturbation. So, I mean, it just started with a blob that was expanding radially outwards, and it generates spiral structure. Planets generate spiral arms in a disk in a slightly different way. It's a bit more complicated. So the way that it's done is that it's not just like one wave being generated by a planet. There's a series of waves that are being generated by a planet that interfere with one another and generate a spiral wake. So if you take a Fourier decomposition of the planet's potential, you can generate the waves that each of these components makes, and then they interfere with one another to make the spiral wake. So planets can make spiral arms. Planets can also generate gaps in the dust distribution. So left is the gas component, the right is millimeter roughly sized dust grains. You can see that planets also generate gaps in the dust. They can do this in two ways. In this example here, the dust grains are basically being torqued by the planet. So a dust grain on the outside of the planet has got, it basically gets pulled forward by the planet, and so it gains angular momentum, and so it moves to a higher orbit. The dust grains inside the planet's orbit get dragged or pulled back, so they lose angular momentum, so they fall inwards a bit more. You can also generate gaps in disks. The planets can generate gaps in disks by carving a gap in the gas, and that will create a pressure maximum outside of the planet's orbit, and that pressure maximum will trap dust grains as well. So in the case of PDS 70, that's exactly what's happening. Planets can also generate cavities. If you have a sufficiently large planet, you can carve a really deep gap. And this gap, the gap edge can become Rossby wave unstable and basically generate vortices. So imagine you have a Kelvin-Helmholtz instability, you've got shear, and you start generating vortices. The Rossby wave instability is essentially the same thing, but in a rotating frame. So with this gas overdensity orbiting around, you can potentially trap dust grains in this overdensity and make these horseshoe features that we see. Alrighty, how are we doing on? Another way to generate cavities and these horseshoe features is with stellar companions. So these simulations have got a 0.1 mass ratio companion. So think 1 solar mass primary star, a 0.1 solar mass companion. And then on the right, it's twice as high a mass. You can generate eccentric cavities. You can generate very strong perturbations in the disk, lots of spiral arms. And in the case of the high mass ratios, you can generate this overdense lump that's orbiting around the cavity. So that's also another contender for explaining for example, the dust horseshoe that I showed earlier. There's multiple ways of generating a similar morphology. But the important piece of information that we also get is the velocity field of the disks. This is just a snapshot of a simulation with a planet in it, and we're looking at the radial velocity in the midplane of the disk. What you're seeing here is the spiral wake generated by the planet. That's here. The wake propagates outwards and inwards, and it generates perturbations in the velocity field of the disk by on the order of a few hundred meters per second. The azimuthal component is fairly minor. This whole red area here is basically because the whole disk itself is orbiting at sub-Keplerian speed because of the gas pressure support. So the gas is supporting some of the rotation. Stellar companions, on the other hand, make quite a lot more mess. So note that the color bar here is a factor of 3 higher. So we can generate perturbations on the order of kilometers per second. The spiral wakes out here are about on the same order as what we see from a planet. But inside of the cavity, the gas gets flung around a lot by the stellar companion. I don't think that's much of a surprise. So just a very quick definition. The way that we see these perturbations in a disk in observations, they manifest themselves as kinks in the. So these lines here are isovelocity curves. The disk is in Keplerian rotation, and so if there's no perturbation, these isovelocity curves should be smooth. But if there's a localized distortion in the velocity field, it manifests itself as a kink. So as an example here, this material in red is moving towards the observer. And so this is the red-shifted side. Let me make sure I'm getting this right. It's the red-shifted side. It's moving slower. So this is where the projected line of sight velocity of the disk is 0. And so it's moving slower. So it moves towards that v equals 0 line. So planets make these kinks, and we actually have a few examples of disks where we have found these kinks. The first example that was published is this disk known as HD 163296, and you can see in this circle area here, there's a localized kink right in this area just here, and as in the single channel of isovelocity curve snapshot, you can see that there's a very slight perturbation. If the disk was unperturbed, then the emission should be following this curved dotted line. But at this one particular location, it deviates. And this is work done by Christoph Pint here at Monash, along with Daniel Price. So what we have here is a confirmed detection of a planet located in a disk. But we also have more than just that. You might notice down here on the bottom right, there's some additional kinks here as well. All right. So we can create a model and basically try and reproduce the features that we see in HD 163. So the left is observations, the right is a model with a 2 Jupiter mass planet. And you can see that the planet produces a kink quite similar to what we see in the observations. But there's also additional features that we see in the disk additional kinks that we can see in the disk as well. So you see on the bottom here, I'm pointing out one particular kink that travels along this direction in the disk. So what this is actually the spiral wake from the planet. It's propagated around. So we have the kink from the planet and then the spiral wake that's traveling around the opposite side of the disk and is perturbing the velocity field on the other side of the disk. So on the right here is an analytic prediction of the amplitude of this kink. and where it should fall, where it should lie in the disk. So it's being projected to it's being projected to the surface layer of the disk where the CO emission is emitting from. And you can see that we expect the kink to travel around the disk, and then right where we see the velocity kink in the observations, it lines up very well where we would expect the additional kinks from the wake itself. So this is a first detection of a wake being generated by a planet. So we have examples where we've found accreting planets and protoplanetary disks, but we haven't had an example where we have a spiral arm and a planet. So we haven't got any examples where we've seen spiral arms and directly linked it to a planet. The only case that we have that is what I showed earlier, HD 100-453, where you have this cavity, these spiral arms, and there's a companion on the outside. So this is a first detection. The velocity, the amplitude of this velocity here across the wake is like static. The only thing that changes is the position of the planet. So as the planet orbits around, the kink amplitude itself doesn't change. What's shown here is like we have one observation and we're looking at different slices of velocity. There's like no time variation here. It's like look at this disk, get an image, and we have each pixel has like a spectrum, and we're just looking at the emission from each pixel. You can actually see the kink directly in the velocity map. So it's a bit easier to see on the southern side down here, but there's these little perturbations in the velocity map that are consistent with where the kink location, where we expect it to be. And we can see similar things if we produce an analytic model. This is work largely done by Tom here in the audience. Or if we run a hydrodynamic simulation and do radiative transfer to produce CO observations, images, and generate the velocity field from that, we can see a similar thing. Another way that you can try and look for the kink as well is to take so you have the velocity map of the velocity field. You can fit that velocity field by, what's the stellar mass, the mass of the object in the center, what's the emitting layer that the CO emission's coming from, what's the inclination of the disk, etc. And you can fit a model and then subtract that model and get the residuals from the model. So that's what's shown here for the observations here on the right from synthetic observations of my model and just directly from the model. So you can see as well in here that there's a deviation in the residuals that's consistent with the location of the wake as well. And finally, we can also see the wake in the total intensity. So how bright the intensity of the CO. It's a bit more tentative, but so the planet is located here. And as the wake's traveling around, you don't see the emission really here, but there's an excess of emission on the southern side down here that is co-located with the perturbation in the velocity. So the cool thing about this is the way that the spiral wake propagates through the disk is dependent on the properties of the disk itself. It travels at a different speed in a warmer disk than it does in a cooler disk. So by obtaining, so it allows us to essentially measure features of the disk. So we can measure how hot the disk is. And given that we know we can also obtain the mass of the planet from the velocity kink, we can use that information to constrain, for example, accretion, models of accretion on the protoplanets. So in PDS-70, we don't know the mass of those planets very well. We get the mass from accretion models. But in this case, we know the mass very well. So if we can get a measurement of the accretion rate of this planet, we can then break an important degeneracy in accretion disk models. But this planet also raises quite a few questions. The location is 250 AU away from the central star. In the core accretion paradigm, you need time, you need orbits for the body around to generate pebbles and to obtain, accrete pebbles and build the mass of the central core. But this is at 250 AU, this planet. This is very far away. And core accretion is not very efficient out there. So it raises the question, did this planet form closer to the star and then migrate outwards somehow? Was it produced by some other mechanism of planet formation, such as gravitational instability? This planet is quite massive. It's 2 times the mass of Jupiter, roughly. And a planet that massive should be, if there is any dust in the outer disk, it should be halting the migration of that dust from moving inwards. But we don't see any ring of material, no dust rings. So it's a bit peculiar that you need a lot of dust to make a planet, but there's also no dust where the planet is. I think it's a little bit of a conundrum. And there's no detection of the circumplanetary disk yet, but hopefully with JWST, we will be able to detect it. Okay, stuck. Okay, so now I'm going to move on to, instead of planets, we're going to start talking about stellar companions. So here's an example of this is my first work in the field of planet formation. We have this disk known as IRS-48. In 2013, there was observations that showed that it had this large dust horseshoe in the continuum emission. And at the time, it was very peculiar. It was the first such detection, I believe. And this kind of lended credence to the idea of planets generating or carving deep gaps and generating vortices and making these asymmetries. But we have additional information on this source, such as the velocity field, that show that there's strong perturbations in the disk. So there was this idea, like I said, that vortices could be generated around the outer gap carved by a planet and concentrate dust grains. And this idea does work pretty well. I mean, you can concentrate dust in large amounts and make this sort of lopsided horseshoe feature that we see. But it's not the only explanation. So here I have a simulation where the central star is 2 solar mass. The companion here on the outside is 0.4, so it's a mass ratio of 0.2. It generates this overdense feature that's orbiting around this central cavity, and over time this cavity size is growing. That outer white ring is roughly the distance of the overdense feature in IRS-48. So we can also we can generate these overdense features also in a circumbinary disk. It doesn't just have to be in a planet hosting disk. So that keeps going, but here I've taken a snapshot of the simulation and added dust grains into it. There wasn't dust grains in it originally because they're quite expensive to run, but here I've just added in dust grains proportional to the density of gas, and then let that evolve over time. And you can see that those dust grains start concentrating inside this overdense feature with time. And I've run this for multiple grain sizes. So here on the left is 100 micron, and then right is 1 millimeter sized dust grains. So with an increasing dust grain size, the concentration becomes more efficient. And that is also seen in the observations of IRS-48, where so 440 micron here and then 7 millimeter. So with the larger dust grain sizes, the dust trap in IRS-48 becomes more azimuthally concentrated. So even though this is a bigger beam size here, you can quite clearly see that the azimuthal extent of the dust trap is not as great as it is in the smaller dust grains. And that's also what we can see in the simulation. But the most important thing for these disks is to differentiate between these two models. So we have these two competing models. Is there a stellar companion in IRS-48, or is there a planet generating a vortex? On the top row here is the predictions for IRS-48 by Huang et al. Of what the kinematics should look like if it's a planet hosting disk and it's generating a vortex. On the bottom are the channel maps from IRS-48. So these are like the isovelocity curves. You're looking at the disk, like a segmented image of the disk at different velocities. So if you were to add all of these velocities together, you'd get a picture of the disk. So you can see in IRS-48, although the signal to noise is not very good on the observations, that there's pretty strong perturbations in the isovelocity curves. This channel here corresponds with the rest velocity of the disk. So when the disk is at rest along our line of sight, or the portion of the disk that's at rest along our line of sight, these lines here should be pointing straight up and down. They shouldn't be curved like this. And that's not seen in the planet predictions. So here are my predictions from if IRS-48 is a circumbinary disk. The top row is observations, middle row is my simulation, and noise has been added so it's on a similar level to the observations. And you can see that this deflection of the isovelocity curves is recovered. The reason why that deflection is there at all is that the disk itself is eccentric, and we're looking at it kind of off angle. We're looking at the disk. We're looking at one side of the disk that's moving a lot faster than it should be. So if it was in a circular orbit, not eccentric, then that material wouldn't be moving as fast as it is. So the circumbinary disk model does a much better job of recreating the velocity map of IRS-48. And here's, instead of the channel maps, just a pure velocity map. Disk material inside of the cavity here gets accelerated very strongly due to the binary, so we should also see this in IRS-48. And we kind of do. So to summarize for IRS-48, a circumbinary disk model does a better job at reproducing, most importantly, the velocity information. The planet model doesn't reproduce it. So another example we're going to talk about is AB Aurigae. So this is a disk that, it's got all of these spiral arms. There's material falling in onto it and potentially perturbing the disk. So on the left is the scattered light image. On the right here is the millimeter wavelength images. So we see that there's a big cavity. There's a dust asymmetry, kind of not as large as IRS-48, but it's there. And in the white contours here are spiral arms seen in carbon monoxide. You might have seen recently in press earlier this year a claimed detection of a protoplanet in AB Aurigae by Curry et al. And so this is a total intensity image of the disk. And you can see this bright spot just down here on the south. I'm almost certainly biased, but there's reasons to be quite skeptical of this detection. First of all is the best fit orbit of this object. So there's enough epochs that we can fit in orbit to this object, and it's somehow inclined 25 to 60 degrees away from the plane of the disk. It's highly eccentric, but when we're seeing it, it's somehow still embedded in the disk. So it's highly eccentric, highly inclined, but also embedded, and very massive. It's so massive, in fact, that it's quite confusing how such a massive object is embedded, because it should be clearing out the material and generating a cavity. There's no convincing detection of accretion, so there is additional H alpha emission down in this region, but it's not clear if that's H alpha emission scattering off of the disk, because you also see lots of H alpha all throughout the disk in regions that are excessively bright, like this spiral arm here. So I did work with Pedro Poblete, and we were convinced that all of the features of AB Righe are more consistent with it being a binary, circumbinary disk rather than a planet hosting disk. So this is a snapshot from our work, our simulation, where we have an inclined stellar companion. The companion's generating a cavity, but it's also generating these strong spiral arms. The blue and white that you see here are the best fit spirals to the spirals seen in carbon monoxide. And we're just looking at changes in the phase of the binary orbit. And at a particular time, say 0.6, 0.7, we get the best match to the spiral arms. So on the right column here are the observations. We have the spiral arms seen in carbon monoxide here and here. Also, we have the velocity field, and you can see very clearly that it's very strongly perturbed. So that's easy to recreate for a circumbinary disk model, but it's not for a planet model. So we can reproduce the spiral arms. We can also reproduce the perturbed kinematics. But so far, there's no detection of this stellar companion. So that's until obviously we find something, we can't say for sure that this is what's going on in this disk, but it does seem quite plausible. So I've kind of just gone a bit hand-wavy over these examples of protoplanetary disks where, you know, I can run a model and I can recreate things, but it's not very quantitative, right? It's just like qualitatively matching images. So is there a way that we can more quantitatively go look at a disk and go, is it likely to be a planet hosting disk, or is it likely to be a circumbinary disk? So this is work I've been doing more recently. So just to kind of highlight the differences between a circumbinary disk and a planet hosting disk. The top row here is, this is a surface density from a simulation. And then this is what the 12 CO isotope log of carbon monoxide should look like. And then 13 CO and C18O. So these are progressively less abundant isotopologues of carbon monoxide. And the less abundant isotopologues start to more faithfully trace the surface density profile of the disk. So this is like, this here is mostly showing you how hot everything is. So everything's very bright around the central star. But over here, it's more showing you where the surface density is. And one feature that you can quite clearly see from here is that circumbinary disks should have very strongly gas-depleted central cavities. Whereas even a disk with two fairly large planets in it struggles to clear out a central cavity. And we can also look at the kinematics of these examples. So here's a multiple planet simulation. You do see some very minor kinks, which we expect from planets to generate, but there's quite a remarkable difference between the planet hosting disk and the circumbinary disk, where we see these very strongly perturbed kinematics, as I showed in the simulation earlier. We see deviations on the order of kilometers per second rather than hundreds of meters per second. So this is another morphological feature that we can go look at a disk. Okay, is there really strong perturbations in the disk? We can also look at the velocity maps of the disk, and we can try and look for certain features that we only see in a circumbinary disk and not in a planet hosting disk. So in the planet hosting disk, the kinematics are relatively smooth, but in the circumbinary disks, they're strongly perturbed. So we can take features of the velocity maps and devise some criteria to measure how perturbed it is. And there's two ways that I thought of doing this. The first way is that you can look just purely at the velocities. So we look at the velocity from the red shifted side, the velocity from the blue shifted side, and we just take like a weighted ratio of those two values. In an unperturbed disk, this ratio should be close to 0, or even a planet hosting disk, because the perturbations are small. But in a strongly perturbed disk, this quantity will be large. Not only can we just look at the total velocity of the velocities of the disk, but we can also look at the area that some particular velocity is encapsulating. So for example, here in the polar companion, this one down here, you can see that there's a lot more redshifted, highly redshifted material than there is blue shifted material. So if we draw like a circle around that, and then compare with how much material is moving of a similar velocity on the other side of the disk, we can use that information as well to define our ratios. So I call these a velocity ratio and a velocity area, and then we can run a whole bunch of simulations and measure these values in the simulations, and we find that there's a very clear distinction between the two populations of circumbinary versus planet hosting disks. So on the right here, these are all of the circumbinary disks, and on the left is there's a planet hosting disk, there's a disk with no planet, and there's a disk with multiple planets in it. And we can see that the population is very evenly split, at least when we do it in simulations. But reality is, of course, a lot more complicated. We don't observe every disk in the same way, so we get more time on some disks than others. Some disks are brighter, so we get better signal to noise for some given amount of time. Some are bigger, and so we can resolve them better. But this distinction at least holds up fairly well for the observing criteria that we can get with that is readily obtainable these days. So here, I've essentially done the same thing. I've measured these these criteria on different disks in the literature. Down the bottom left here, there's a black dot here that's a bit hard to see, and then this pink dot. These are all disks that we suspect are planet hosting. In fact, one of them is confirmed to be planet hosting. It's the disk I showed earlier where we've mapped the planetary wake. And we can see that that disk falls quite comfortably in the region that we would expect it to if it weren't a circumbinary disk. The purple dot on the right is GG tau, the disk that I showed earlier. It shows strong perturbations. We know it's more than a binary. And in between are other disks that we suspect are binaries or we know are binaries. But the quality of the observations that we have of those disks so far is not very robust. And so it's a bit more tentative on some of these. So another cool thing about these criteria is that, the best way to tell whether something's a binary or not if you can't see the companion is to look for the astrometric signature of, the bright star at least wobbling from the companion. So that's what Gaia is really good at doing. It can do it for planetary mass objects, so finding binaries should be pretty easy for ALMA, right? But it's kind of complicated in the fact that these are not isolated stars. They have disk material around them, so even a single star can look like it's wobbling to Gaia and look like that it has a companion when it in fact doesn't, just because of all the disk material around it. But here anyway is what my criteria on the bottom right, on the bottom panel. So this is the ratio quantity and the area quantity, and these are versus the astrometric fit provided by Gaia. So a large value of this astrometric fit indicates that it's a poor fit. So it's the higher you are on this line, on this axis, the more inconsistent the star is with being a single star. So it's more likely to be a binary. And we can see that the criteria from the velocity maps correlates quite strongly with what Gaia sees. And with the very little amount of time I have left, I'm going to talk very briefly about some of the work that's being done at Los Alamos. So our group has been looking at binary black holes embedded in AGN disks. So here's just a cartoonish drawing. It's suspected that AGN disks around supermassive black holes contain a large population of black holes that can either form within the disk itself due to gravitational instability of gas disk material collapsing under gravity, or by stars or black holes being captured in the AGN disk from the nuclear cluster. So there's this population that is thought to exist of black holes, right? So it's a potential area where we could find gravitational wave or expect gravitational wave sources. Conventionally, people have kind of thought that to get two black holes close enough where gravitational wave emission becomes important, you can't do that with two isolated black holes. You need something to take the energy away from the binary. And so one way you can do that is by throwing in a third body and have some third body interaction that the third body gets ejected and it causes the binary to harden. But fortunately, if you're in a disk, there's plenty of material around that's going to do that for you. That's the gas material. So one of the grad students at Cornell, but he was with us for a year, Jaro Lee, he started running some simulations where we have this is a movie, it should, okay. Basically the setup is we have an AGN disk, you have two planets, planetary mass objects, they're really, black holes. You let them carve a gap in the disk, and then they're on fixed orbits, but then you release them once the disk itself has reached a quasi-steady state. And this movie plays at least. So what's happening here is those two black holes are coming close to one another and interacting, and the disk around them is interacting and causing the binary to harden. If this was just an n-body simulation, you wouldn't get this kind of damping. You might form a temporary binary, but the tidal forces from the central AGN are eventually going to disrupt them. But what happens in this case when you have a disk around each object is, each black hole is carrying a disk. Those disks collide with one another and they dissipate all of their kinetic energy into shocks. And so they lose their kinetic energy, they kind of sit stationary once they collide. The black holes, on the other hand, don't really care about what the gas is doing, so they just travel through the gas. And so they, at first, just plow through the gas. But what happens is, when this replays from the beginning, when you have all of this disk material that shocks and gets stuck in the middle, it starts pulling back on the black holes. So this plot on the right here is the energy of the binary with time, the potential and the kinetic. So at first, the energy is relatively conserved until the Circum single disks here meet each other. When they meet each other, the black holes start to try and pull away from that leftover disk material, but the disk material is starting to pull back on them. And so they lose energy as they move away. And then this process just essentially keeps going and forces the binaries to harden. So if the black holes are there and there's enough of them that these interactions are frequent enough, it seems quite easy to form these binaries inside of an AGN disk. And it obviously opens up the possibility of there being electromagnetic counterparts to this formation mechanism as well. I'm just going to gloss over this. So just a very one slide take-home message, since we've got very little time left. What we've found from our binary black hole simulations is that it's very, very easy to make these black holes merge in an AGN disk. So the hardest ones to make merge are the equal mass, non-eccentric circular orbit black holes. These want to expand. But if you start changing anything about them at all, like the mass ratio or the eccentricity, that starts to force them to merge. We've also done simulations where we say that each black hole is heating the disk material around it, and found that as long as the CSD of the black holes is about 3 times warmer than the material around them, then they'll merge. So top panel here is just temperature. So this is just a parametric way of setting the temperature in the disk. So this is like 40 times, the CSD is 40 times hotter than the background disk. And then this gamma here is like how fast does it slope off? So if you have something very steep, you obviously, if the temperature drops very quickly, the CSDs need to be a lot hotter. But as long as the CSD is about 3 times warmer than the surrounding material, then they merge. But there becomes a point where they get close enough to each other where it's not quite clear if this mechanism works anymore. So if the black holes are really close, they're almost like isolated binaries. And it's not quite clear if this works or not. Just purely because in the isolated binary case, people find that the binaries tend to expand. And so, but this is a bit different. Since they're embedded in a disk, there's going to be accretion material coming from different directions from above the plane of the disk. Anyway, that's it. Thank you.
Maybe I can ask you maybe a bit IRS-48. I think it's kind of related also to the feedback here because it also mentioned kind of expansion contraction. So when you're doing the simulations for IRS-48, do you take into account the feedback from the both gas and dust in the disk?
Onto the binary?
Yeah, to the binary.
Yes, but the disk mass is so low that the change in the orbital elements of the binary is small. I mean, I've run the simulation for about 1,000 orbits, and the feedback is quite small. Over the lifetime of the disk, it might be important.
I'm just curious about the direction of the torque, if it's like kind of consistent with the typical pictures of.
Oh, okay. So whether the binary wants to contract or expand, it wants to contract. I think that's mainly because what drives the binary apart is the Circum single disks, and we don't resolve them in the simulation. The particles get eaten up by the sink.
Curious, I didn't know much about the merging of black holes in AGN disks.
Yep.
I mean, is that expected to be a fairly significant channel for gravitational wave events, or is it sort of just that it's a place, yes, it's enhanced, but it's only a small addition to the background of overall events?
It really depends what you assume about the black hole distribution in the AGN disk. I mean, the general thought in the field is that it is enough to explain the frequency of gravitational wave sources that we detect. And I mean, this hasn't been done with hydro, but if you take an n-body simulation and put in some prescription for what the gas drag does to the black hole, then the rates of mergers is consistent with what we see. But I'm not familiar with how realistic the assumptions are about how densely packed the AGN disk is. There is ways kind of to alleviate that though, because in typical AGN disk models, there's changes in the disk parameters that change how the black holes migrate. So generally in like a protoplanetary disk, everything wants to migrate inwards. But if you have a sudden change in the temperature or the opacity of the disk, you can get a migration trap. And so everything will eventually migrate to this particular radius. And even if there's only a small amount of objects, they're going to interact with each other very frequently. So the thought about these is that you form these binaries in that migration trap. But then the counterpoint to that, sorry, I'll just leave it there. Yeah.
You stressed a lot the need, to have a perturber, so either a planet or another star
Mm-hmm.
to create these structures in the disk. But my question is it really necessary, or are these disks sufficiently unstable that just their normal grayness is enough to excite wave, for example? In the background, I know nothing about the planetary disk, but in galaxies, you don't really need that, right? Disks are gravitationally stable, but kind of Q2 rate roughly 1.
Yeah.
And then these things occur more or less spontaneously. The perturber can be really minimal.
Yeah. So for some of the perturbations we see, they're so strong that that they should be shocking, right? There should be shocks going on that's going to dissipate any energy, any perturbation that you might have in the disk. So you need a way to continually generate these perturbations. Otherwise, they should dissipate on dynamical timescales. And for protoplanetary disks, that's only one dynamical timescale might only be 100 to 1,000 years. Depending on where you are on the disk, or much shorter, tens of years. So there needs to be a way to continually generate these perturbations, otherwise the disk should just not, we shouldn't see them.
Do you have a question?
Yeah, thank you. Thanks for the very nice talk. So I'm still a little bit puzzled by the gas in the AGN binary black hole merger scenario. The gas that each black hole sort of carries with it, ending up in the center there, right? So this is all happening inside a fairly hot AGN disk, right? So I'm actually curious why this overdensity would stay around in this case, right? It's not. I mean, the simulation you showed sort of showed, these two parcels of gas around the two black holes and kind of nothing in the background, right?
Right.
You do have this background, right? Is this background not wreaking havoc with what's going on, and also is it not just changing the how much mass can the black hole actually carry, because your essentially your bonding radius is set by the fairly high sound speed in the AGN disk, right? So this overdensity is it really that significant in terms of the total mass?
Well, so the models that we've done so far are obviously very simplified, assuming isothermal equation of state and a non-turbulent disk background. But so part of it is you won't form these binaries if the disk mass is sufficiently low. So the disk mass to binary black hole mass ratio needs to be sufficiently high for this mechanism to work. Otherwise, it's just like being in the n-body case, where you might form a temporary binary, but it will get disrupted by the tidal forces from the AGN. So I guess there's a lot of wiggle room for where these mergers can happen. Like it could happen within 1,000 Rg maybe of the AGN, but it could also be at the very outer regions of the disk where things might not be so hot and turbulent. It depends sensitively on well, there's plenty of AGN disk models out there. So the room of the background disk can be doing a lot of different things, and that would just still be entirely consistent with what we think we know about AGN disks. And like another thing about that is, maybe the disk is a lot more puffy than we think it is, so these black holes won't carve gaps. But I don't suspect that would change the picture very much. As long as they can form CSDs though. The CSDs are the important part because that's what's going to dampen the energy from the interaction.